Okay, so if you remember, the ratio test and the root tests both have this inconclusive possibility. So when does that happen? Maybe take a minute just to remember that. Well, the ratio test is this limit. It's the limit as n goes to infinity of an plus 1 over an, taking the absolute value. And it comes out to equal some value r. And our root test is the limit as n goes to infinity of nth root of the absolute value of an, and we give it the name r, whatever that comes out to. And this is inconclusive when r is going to be equal to 1, right? Remember, the meaning of r in these tests is like the r of a geometric series. So the tests say that approximately the series being tested behaves like a geometric series with this value of r. And when r is equal to 1, the test is not sensitive enough to distinguish between geometric series where r value is less than 1, geometric series where r value is greater than 1, because r is the cusp between convergent and divergent geometric series. R equals 1 is that cutoff. Okay, so we have to remember some basic rules about which types of functions are going to give you an r value of 1. Basically, it hinges on the fact that if you take a limit of a rational function, then it's really just the leading coefficients that determine your result. So notice this guy right here. The first example right here, this is a rational function. That means that if I set up a ratio test, I'm going to be taking a limit of two polynomials, one in the numerator, one in the denominator, and both will have the exact same degree, and both will have the exact same leading coefficient. Go ahead and try it out. I mean, just set up the ratio test and do it for this guy. It's going to lead to an r value of 1. Okay, so that's easy to show for any rational function. So actually, it turns out that the root test will also do the same thing, because for the root test, you'd be imagining this, right? Nth root, oops, nth root. And these are both facts that we just reviewed in previous examples. The nth root of 2 is going to go to 1. The nth root of n to the 4th is going to go to 1 as well. We actually did the nth root of n cubed earlier, but makes no difference. It's still an nth root of a power. So both tests lead to an r of 1, meaning we get an inconclusive result right here. So what's the lesson here? Never use the ratio test and the root test for terms that are defined by a rational function. Okay, moving on to the next one. This one, n squared over 2 to the n, is, I guess, what I would call the textbook example of something that works well with the ratio test and root tests. Okay, powers mixed with exponentials work great for both tests. Powers, like n squared, I should be careful right here, together with, as long as they appear together with exponentials, the exponential in this problem being 2 to the n, right? So as long as these appear together, these are perfect for the both tests. Okay, and will give a conclusive result. In fact, if you want to study this problem on your own, we will in fact get an R value of 1/2, both tests, okay? All right, let's move on to the next one. Here we have a -3 to the n plus 1 and power n cubed in the denominator. This is again a combination of power and an exponential. And what did I just say? Powers together with exponentials work well for both tests. So this will work out just fine. I suggest you go through and do this one self-study because there are negative signs right here to worry about. And you should find that what you end up with is answer with them saying that this series behaves roughly like a geometric series with the absolute value of R equals 3. And so both tests end up being conclusive. In fact, we could also say it's divergent. Oh, and in the previous problem, I guess I should have labeled that convergent. Okay. Last problem here. This is what we would call an algebraic function. Algebraic function is a combination of root extraction together with the operations of a rational function. So it's basically a rational function, but where you allow fractional powers. That's a 1/2 power of n, right? So instead of integer powers, now you allow fractional powers, and that's an algebraic function. And this is also an example where both tests will always give an R of 1, and meaning they will be inconclusive. So again, I suggest you try it out. Self-study. And when you work the problem, pay attention to why this would be the case for any algebraic function. Same thing back up here with this problem. Self-study, work it out, show that R is going to be equal to 1, and pay attention to why that would work out the same for any other rational function. By the way, it turns out that we should probably talk about how do you test these series for convergence, right? What should you do for this series and what should you do for this series? Well, I hope the first one is obvious. This series right here is just twice a p series, right? So you memorized how p series behave, right? P series with p equals 4 greater than 1, that's a convergent series. And this one down here, what should we do with this one? This one isn't quite a p series, is it? But it does have n cubed in the denominator and an n to the 1/2 in the numerator. So what this is saying is that it's like the series where you'd have an n to the 1/2 and an n cubed, which would basically give us n to the 5/2 in the denominator. So what are we looking at here? This is behaving like a p series with p equals 5/2, but it's not a p series with p equals 5/2. So what do? Comparison test. Right? That's how all these series work. Practice with them, and they're really not that difficult. It's just a matter of knowing your tools. You can't just attack every problem with a hammer. It doesn't work for getting some jobs done. Same thing here. The comparison test, root test, ratio test, they all work well for their specific uses, but it's a matter of learning that. What are their uses? Where do they work well?